Welcome to 11.1 and 11.2, Introduction to Arithmetic and Geometric Sequences. So I went ahead and filled in the chart. If you look at the graph on the right, it's a typical line, and I filled in the table of values. Well, what you'll notice is the slope is 2, and I wrote the equation in point-slope form. Now, if I wanted to go to slope-intercept form, we could quickly convert that y equals 2x plus 1 algebraically, or we could just look at the graph and see it has a y-intercept of 1 and a slope of 2. But I want to use that as a lead-in to arithmetic sequences. A table of values for an equation of a line can also be thought of as an arithmetic sequence. An arithmetic sequence is a list of numbers that increase by adding or subtracting the same number, called the common difference, denoted with a d, to the previous number, i.e. the slope. The table of values can be written x comma y into n comma t sub n, where n is the place in the sequence and t sub n is the actual term or value of the sequence. For instance, let's write it down. In the table above, we have the numbers 1 through 7, which are the x values. Those would be the n, because that's the place value, the spot in the sequence. And t sub n would be 3, 5, 7, 9, 11, 13, 15. Using our sequence, we would recognize that d, the common difference, is 2. Now, when we think about the common difference, we want to think about taking the second term, 5, for instance, minus the first term, 3. That's how we get 2. T sub 4 would be 9, in case they ask you. So that means in the fourth position, what is the actual number? We can also rewrite our point-slope equation using n, d, and t sub n. So if we take out y, we can put in t sub n equals 3 plus 2 times n minus 1. In general, the formula for an arithmetic sequence is t sub n equals t sub 1 plus d times n minus 1. In a little while, I'm going to show you a very simple way to do it as well. So example 1, given the sequence 17, 25, 33, ... to 305. So we know the sequence ends at 305. We just don't know how many terms are in between 33 and 305. So let's find a formula to represent this. This formula that we're going to run is called explicit. Next year, you'll get into what's called recursive formulas as well. So explicit formulas are basically formulas that will, when you input a number, it will output the term or the number in the sequence. So we know t sub n equals 17, that's the first term, plus the common difference, it's going up by 8, times n minus 1. Now all we have to do is the algebra. T sub n equals 17 plus 8n minus 8. So t sub n equals 8n plus 9. However, I wanted to show you a really quick, easy way that I learned to do this. And it goes back to the bell ringer, which was a linear equation. If you look at this sequence, 17 is the first term. But what would, in theory, what would t sub 0 be? Even though that doesn't exist, t sub 0 would be the term before t1. t1 is 17. So t sub 0 would be 8 less than 17. It would be 9. Well, that's really the y-intercept. So if you look at the slope in this problem is 8, so 8n, and the y-intercept would be 9. So look how fast that is. It's the same exact thing. Think of 8 as slope. Think of 9 as y-intercept. Let's continue. Now find the 20th term. The 20th term is t sub 20. So you just plug it in the formula, 8 times 20 plus 9, and you get 169. How many numbers are in the given sequence? Well, we know the sequence ended with 305, so that was t sub n. We know the first term was 17. We know the difference was 8. And we have n minus 1. So we could use that formula, or we could go right to the formula 305 equals 8n plus 9. Doesn't matter which formulas you want to use, you choose. But if we just do the one on the left, it's kind of the way the book does it. You would get 288 equals 8 times n minus 1. You would divide by 8, you get 36 equals n minus 1. So you would get n equals 37. So there's 37 numbers in this sequence. What if you were given a table of values and you had to find the exponential function? Could you do it? Well, what you'll notice is we're going up by ones in the left-hand column, but in the right-hand column, we're multiplying by 4. So we're multiplying by 4. So that is basically the definition of an exponential when you're multiplying by a common number. So in this equation, we would start off with y equals 3, where we started, times 4 to the x minus 1. Another way to think about that is we could think about what is the number before it. Y equals the number before 3 would be 3/4 times 4 to the x. If we think back to exponential, remember a was our y-intercept, so 3/4, and b was our multiplier. So actually, these are equivalent statements. 3 times 4 to the x minus 1 and 3/4 times 4 to the x would be equivalent using your laws of exponents. An exponential function can be thought of as a geometric sequence. A geometric sequence is a list of numbers that all increase by a constant multiple called the common ratio and denoted with an r. In other words, this would be your b in the y equals a times b to the x. Again, we could replace the x and y notation for n comma t sub n and rewrite the equation as follows. T sub n equals 3 times 4 to the n minus 1. In general, for a geometric sequence, we write t sub n equals t sub 1 times r to the n minus 1. And again, we could also use the exponential notation that I noted above. So let's look at example 2. Given t sub n equals 34,816 and t sub 1 is 17 and r is 2, how many terms are in the sequence? Well, you do 34,816 equals 17 times 2 to the n minus 1. So we would divide by 17, and we would get 2,048 equals 2 to the n minus 1. Now, how do we solve when the exponent is the variable? The n is in the exponent. Well, I'll wait for it, as the moans and groans will probably be coming. We're back to logs, ladies and gentlemen. So log base 2 of 2,048 equals n minus 1. That comes out to 11 equals n minus 1. So n is going to equal 12. At times, the sequence is neither arithmetic nor geometric. These sequences are the most difficult to find a formula. To figure out the formula, look for relationships between the place and the term. So the example is 2, 6, 12, 20, 30, 42, and 56. Find a formula to represent the nth term. Well, what you can notice is 2 is equal to the first spot times 2. Oops, sorry about that. 6 would equal the second spot times 3. 12 would equal the third position or spot times 4. And 20 would equal the fourth position times 5. So now you're starting to see the pattern. T sub n would equal the position n times the position plus 1. So if we wanted to find the 100th term, we're basically looking for the 100th term. We know that we would have, or excuse the 1000th term, we'd have 1,000 times 1,001, which equal 1,000,001,000. Finally, I wanted to teach you about an interesting sequence, a very famous sequence called the Fibonacci sequence. I'm not going to read through all of the paragraph, but you can read it. But we have some function notation. Different texts have the Fibonacci sequence listed differently. But basically, what I want to show you is the Fibonacci sequence. You basically are given the first two terms here and here, and then you add them. So if you add them, you'll get 2. If you add these, you get 5. If you add these, you get 8. So basically, you take the two terms before it, and you add them. So here's some challenge problems I want you to try. Go ahead and pause the video and see if you can figure them out. Okay, for the first one, t of 85 is 2,270.6051, and t sub 1 equals 17. Find r. You may be saying, I don't know which formula to use, arithmetic or geometric. Because they said find r, you know it's geometric. So if you use the formula, all you do is input t sub n, you input t sub 1, you're looking for r, and you know it's n minus 1. So it's 85 minus 1, because we know t sub n is t sub 85. So now we can solve this. We're going to divide by 17. And then you may say, well, how do we solve when the bases are? We wouldn't want to do logs. If you remember from the exponential and logarithmic chapter, you want to raise both sides to the 1 over 84 power. And when you do that, you get 1.06 equals r. Number 2. Pause the video, see if you can figure it out. Okay, this is the most difficult problem. You can see my work that I've put down. Let me walk you through how I found this. So find the number of multiples of 7 above 30 and below 300 for the sequence 35 to 294. So we don't know exactly where 294 ends, and we don't know how many there are. That's what we're trying to figure out. We know 35 is a multiple of 7, and 294 is a multiple of 7. The common mistake here is that multiples, people think it's geometric. If you think about the definition of multiplication, you're basically adding a certain number each time successively. So therefore, it's an arithmetic sequence. So if you know that on the left-hand side, method 1, it's more algebraic, more formulaic kind of thing. You can say 294 is my t sub n, 35 is my t sub 1. I know that I'm going to be going up by 7s because that's the definition of being a multiple of 7. And then I just algebraically manipulate the problem and get 38. An interesting way of thinking about it is conceptual. You know that you want to figure out how many multiples are between 30 and 300. So what I did was I found the difference between 30 and 300. So that's 270. So within 270 in terms of the distance or the difference, I have to figure out how many 7s I can fit in there. So I take 270 and divide by 7, and I get 38.6. So 38.6 does not round to 39, because remember, we're talking about integers. We're talking about whole integers or whole numbers. I can't count 0.6. So I either have to decide 38 or 39. Well, I don't have enough, 7s to fit into 39, so it's going to end up being 38 numbers is the number of 7s that I can actually fit. That's your notes for today. Good luck on your homework and your Delta Math.